Hey, this is Mr. Ayton. This is Pre-AP Chemistry, and we are in Unit 10, Aqueous Solutions. We're dissolving some stuff, and it's week 22. What are we going to learn in this week? We're going to take a look at how to separate solutions. Yes, now that we have a solution, how do you separate it? How do you get that stuff out of the solution? And we're going to do it with two things, chromatography and distillation. Chromatography and distillation. Also, we're going to take a look at solubility. How do things actually dissolve? What things do dissolve, what things don't dissolve? How soluble are certain substances? And last, we're going to take a look at what's called the Beer's Law Laboratory. Beer's Law Laboratory. So let's first take a look at separating solutions via chromatography. And when we use what's called paper chromatography, we're going to separate solutions by their polarities. So let's take it. Let's say this mobile solvent. So I'm going to call this the mobile solvent. The mobile solvent, let's say, is a polar solution. And the paper itself, which is the non-mobile solvent, that is the stationary, is going to be nonpolar. Okay, so the paper is going to be nonpolar. The solution down here is polar, which means the polar solution will start to move its way up the paper, and it's going to get up to this spot right here, okay? And we're going to call this the solvent front, okay? We're going to call that the solvent front, okay? So let's say we have a little dot right here, a little dot from a marker, and this marker, let's not put it right here. Let's put it at this line right here, this starting line right here. So we're going to put a little dot right here. And this dot has a bunch of different solutions. It's a solution. It's made up of a bunch of different colors. And let's say this blue color, it separates. So as this moves upwards, it separates into blue. And let's say it separates into red. And let's say it separates into green. So what was once a dark black dot, as this started moving up, you can see the blue moved faster than the red, moved faster than the green. Which means if the blue moved the greatest distance, you can see we know the blue is most polar because it was moving with the polar solvent front. Okay, and you can see it moved, if we measure this full distance and we measure how the distance that it went, it moved about 80%. And so we're going to call that the RF value. The RF value shows how far, percentage-wise, a ratio, it moves. It moved 8 parts out of the total 10. Take a look at this red. This red is the next polar. And this red one moved about 50%, didn't it? So we can say the RF value is 0.50, okay? And you can see the green right here moved about, well, let's call it about 30%, okay? 0.30, okay? So you can see that this solution separated, and the green one is the most nonpolar, It's the least polar. And the blue one is the most polar. Now, if your solvent front is a nonpolar, then the solution, the part of the solution that's going to move the most is going to be nonpolar. But here, our solution is polar. So what moved the greatest is the one that could make polar attractions with this polar solvent. Okay? And if we know our percentages, then guess what? If we put our solvent back in, and as we put our solvent back in and we put our little black dot again, let's put our little black dot again right here. And let's say our solvent front only goes this far. Okay, our solvent front only goes that far. Well, guess what? This is still going to separate. The blue is going to separate 80%. The red is going to separate 50%. And the green is going to separate 30%. It's still going to keep the same ratio that it did on this long solvent front that it did in a small solvent front. Okay, it's going to keep the same ratio because they make the same attractions to this solvent. Okay, so that's separating via paper chromatography. We can also separate a solution via distillation. And this is dealing with different boiling points, So this is, let's say you have salt water right here. And of course, you can think about it. Water boils at 100 degrees Celsius, and something like NaCl solid boils at a much, much higher temperature. So you can see if we use a Bunsen burner here, we're going to boil the water off. The water turns into steam. This steam then condenses, okay, or it loses heat to this cooling water. And what do we get down here is pure distilled water, DiH2O, which doesn't have anything in there, okay? It's just water molecules. And what gets left behind is a bunch of salt, okay? Because the positives and negatives don't boil at this low temperature of 100 degrees, and they come back together and they make a solid salt. And this is how we make distilled water. This is how we distill something, and that's separating solutions via boiling points, whereas chromatography was separating via polarity, okay? Well, let's take a look at things that are soluble. Well, how do we know if something is soluble with water, if water is our solvent, is it's going to make attractions with the water molecules, or the water molecules will make attractions with the molecule. And you can see here, this water makes hydrogen bonding attractions with this hydrogen right here on this OH part of the molecule. The water can make more hydrogen bonding attractions right here. And so you can see here we have C double bond O. This is to OH. So this can form hydrogen bonding attractions. This C double bond O, we have CH3 on this side. This C double bond O is only dipole attractions. This can only form dipole attractions. A little bit weaker attractions, but still attractions nonetheless, but dipole to dipole attractions. The water molecules can't make these attractions around the CH because the CH part is nonpolar part of the molecule. And so you can see it'll make slight London dispersion force attractions, but this molecule, this CH3COOH, is very soluble in water. Why is it very soluble in water? It can make hydrogen bonding attractions with the water molecules and some dipole-to-dipole attractions with the water molecules as well. Okay, let's take a look at the solubility of a salt in water. Okay, does salt dissolve in water? Well, yes, it has a spectator ion, and this can form attractions with the water molecules. You can see the negative part and the negative part and the negative part of the water attracts the positive ion of the Na+. Whereas the positive parts of the water molecule, of the polar water molecule, the positive parts, and the positive parts, these attract the chloride, okay? And we call these attractions ion to dipole attractions. Ion to dipole attractions. So the salt dissolved in water, it's very soluble in water because it can form ion to dipole attractions. And that makes sense, an ion to a dipole. And that is the attraction. Well, guess what? Something like C6H6, benzene here, will not. This is going to be nonpolar. This is what we call insoluble because this cannot form hydrogen bonding attractions. It can form dipole-dipole attractions. It can form ion-to-dipole attractions. All can form is very instantaneous, slight London dispersion forces. So C6H6 would be very insoluble in water or not able to be dissolved. It's kind of like having oil and water together. They don't mix, except for slight interactions of London dispersion forces. Okay. Last thing is what's called the Beer's Law Laboratory. Beer's Law Laboratory is using what's called colorimetry or spectrophotometry. Colorimetry or spectrophotometry is taking a look at, can we use the color or the absorbance of light to find out what the concentration is? So I don't know the concentration of this copper sulfate solution. So how do I find this unknown molarity of copper sulfate? Well, I have to know known values of copper sulfate. So if you know copper sulfate, you can find something that's unknown. Well, first we got to figure out what wavelength we want to analyze this with. What wavelength of light are we going to shoot into this? What photon of light are we going to shoot into this? And so we're going to put this in a spectrophotometer, and you can see, where does this copper sulfate absorb the most? It has the maximum absorbance at this wavelength right here, about 800, 750, something like that. It's going to be on the red end of the spectrum here. You can see, why doesn't blue absorb? And so this is the absorbance on this y-axis here. Why doesn't blue light absorb this, or why doesn't the solution absorb blue light? Because when we put blue light coming through, the blue solution can't tell the blue solution. It can't absorb anything, and all of it goes straight through. It's kind of like it's colorblind. It's like a clear solution shooting it with clear white light. It can't detect it. But when we shoot it with red light, when we shoot this with a photon of red light, guess what? This can get absorbed by the particles in the solution. And the more particles in the solution, aka more concentrated, the more it will absorb this red light. So once we know at what wavelength we're going to absorb this at, then we can test it at this absorbance level. So we're going to test this at, let's say, 750 nanometers at red light, and we're going to make up a bunch of known solutions. So you can see we have 0 molar and maybe 0.1 molar, and we make up 0.2 molar and all the way up to 0.4 molar or something like that. We're going to make up known solutions. And then we're going to put the known solutions in a little cuvette in what we call a colorimeter. So we're going to put these in a little cuvette, and we're going to put these in what's called a colorimeter. And we're going to shoot it with the light. Okay. Now think about the red light. The red light's going to go straight through something that has no concentration. But the red light's going to get very absorbed in this blue solution. And so you can see we get a graph of concentration versus absorbance. Concentration versus absorbance. You can see when the concentration is 0.2, it absorbs a lot. When the concentration is 0.05, it absorbs very little. And we have a best line fit. We have a best line fit, which means then we can test the unknown solution, this unknown solution. And let's say the unknown solution absorbs at 1. Then we can come over here and we come down and we say, ding, 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 ding. This is a 0.15 molar solution of copper sulfate. So we can only know the unknown if we know a bunch of knowns. And that's called a Beer's Law laboratory or colorimetry. Well, guess what, guys? This was week 22, unit 10, aqueous solutions, all about solutions and everything you would want to know about separating solutions, solubility, as well as Beer's Law. I'll see you guys in class.